So at this stage in organic chemistry, we are really going to shift our focus to more specific reactions. So this is the first of 3 chapters where we're really going to look at compounds containing carbon bonds that are bonded to something that is more electronegative. So in this chapter, what we're really going to look at are alkyl halides. And so these are things that are bonded to or have bonds to the halogens, fluorine, chlorine, bromine, and iodine. That's what we're going to see. We are also going to focus on nucleophilic substitutions in this chapter as well. Now, I've got some what I think are interesting alkyl halides here for you. So, for example, CFCl3 is a refrigerant that's really commonly used, or that was really commonly used, and has been implicated in the issues with the hole in the ozone layer. We have Teflon, which is a non-stick coating that you would find in your pans. Polyvinyl chloride, or PVC, is a plastic that's used in films and pipes and insulation. This is fluticasone, which is used in Flonase. And so without kind of any further ado, let's jump into alkyl halides. Now, alkyl halides, as I mentioned before, are organic molecules that contain a halogen bonded to an sp3 hybridized carbon. The halogen atom in halides is often denoted by this X here, so that's what we're going to use generically. Now, alkyl halides are classified as primary, secondary, and tertiary, depending on the number of carbons bonded to the carbon with the halogen atom. So, for example, right, there are no hydrogens bonded to this one, and it is tertiary. There is 1 hydrogen, and it is secondary, and then there are 2 hydrogens bonded to that carbon, and it is primary. So that's how we classify these. Now, we have some kind of new vocabulary as we talk about alkyl halides. One of the alkyl halides that we'll refer to is a vinyl halide. When you hear people talk about the vinyl group, this is something bonded to a double bond here. You'll also hear people talk about aryl halides. These are halides that are bonded to the aryl group, which is very similar to a benzene group here. These halides are really unreactive in the reactions that are discussed here in Chapter 7, but I bring them up because you find references to vinyl and aryl pretty frequently through literature, and so I just find that it's good for us to know those things. You're also going to see a reference to allylic halides. These have a halogen bonded to a carbon next to a carbon-carbon double bond. And then you're going to have benzylic halides, where that is a halogen bonded to a carbon next to that benzene ring here. So I like to show these next to each other because we can see the vinyl here. It's bonded directly to the double bond, and the allylic is 1 carbon away. Same trend with the aryl and the benzylic here. Now, again, that's just really more vocabulary and being able to understand when something's referred to as vinyl or aryl or benzylic, what we're talking about. But these don't really participate in the reactions that we're going to see in this chapter. Now, we also need to talk about how to name alkyl halides. Naming alkyl halides is very similar to naming alkanes. So the first step is you want to find the parent hydrocarbon chain. Right? And when we do this, the halogen needs to be attached to that parent hydrocarbon chain. So when we look at this example, the hydrocarbon chain would be right there. It's got 7 carbons, so that base name would be heptane. Then we just need to apply all the other rules of nomenclature that we previously learned. Right? So you need to number the chain beginning at the end nearest to the first substituent. So I'm going to come over here and I'm going to say, all right, there's 1, 2, 3, 4, 5, and that's my last substituent. If I number from this side, it's 1, 2, 3, and 2 is lower than 3. And so that's why we go closest to that substituent. And then I need to name the substituents and give their position. Then we're going to alphabetize them. So when we name halogens, chloro is for chlorine, bromo is for bromine, fluoro is for fluorine, and use iota for iodine. So those are kind of our new words that we're going to use here. So when we name this, we would say, okay, the chloro, C comes before M, and so we would say, look, this is 2-chloro, 5-methyl heptane. Okay. So exactly like what we've seen before, we do run into a few common names with this type of, with alkyl halides, and so it's nice to talk about that for just a second. When we talk about common names, right, when you see this, all of the carbon atoms of the molecule are going to be named as a single alkyl group. So for example, this is a tert-butyl group, that would be tert-butyl iodide. This is an ethyl group that a lot of times is referred to as ethyl chloride. These come up frequently with our smaller alkyl halides, but what we are going to stick with in class is using that IUPAC systematic nomenclature. The only reason I bring it up is just in case you were to see, say, a question with that. Now, the properties of alkyl halides dictate their reactivity, specifically the polarity. So alkyl halides are weakly polar molecules. They're going to exhibit dipole-dipole interactions because they have a very polar carbon-halogen bond. Right? And so they're going to have dipole interactions because of the polar bond. Okay. Now, since the rest of the molecules that we're going to look at contain only carbon-carbon and carbon-hydrogen bonds, those are really incapable of intermolecular hydrogen bonding. Okay, so when we look at a bottle, for example, of this molecule, we're not going to see any hydrogen bonding. We're just going to see the dipole-dipole interactions. Now, the electronegative halogen in alkyl halides is what creates that polar bond. Okay, and you can see the electrostatic potential map shown here of 4 really simple alkyl halides. And what we find is that when you look at an alkyl halide, you are going to have an electron deficient site right here at this carbon. And so that means that something that has a lot of electron density, like a nucleophile, can come and attack that carbon. And we see that, right, as this has blue on this side here. Okay. So let's talk about what kinds of reactions alkyl halides will participate in. The 2 biggies are substitution and elimination that we're going to look at. And in this chapter, we are really going to look at substitution reactions. Now, I want to remind you, just refresh your memory about substitution and elimination reactions. In substitution reactions, we have a nucleophile that will take the place of the halogen, right, in this particular reaction with alkyl halides. Then we have an elimination reaction, and in an elimination reaction, the halogen and a proton are removed and a new pi bond is formed. So we're going to focus on this reaction in this chapter and this reaction in the next chapter. So I want to point out one other thing. We are in this chapter going to talk about the difference between a nucleophile and a base and some of the similarities. And I want to remind you that this base is a Bronsted-Lowry base. So without further ado, let's look at substitution reactions. So when we talk about a substitution reaction, you really need three kind of necessary components for this to happen. So the first thing you need for a substitution reaction is that you need an alkyl group containing an sp3 hybridized carbon bonded to a halogen, right? Which in this case, because we're looking at alkyl halides, that's a halogen, but some sort of electronegative atom here shown with an X, okay? Now, the second thing that you need is that X, that is called the leaving group. Right? And that has to be able to accept electron density in this bond when it breaks, right? Because it's going to come over here and it's going to become negative. So it has to be able to accommodate that electron density. The most common are your halogens, right? Where we have some sort of Rx, right? And then you get the X with a negative charge. Or we have ROH2+, where then you get water, right? Or we have RN2+, where you get nitrogen, okay? Then the third thing you need is a nucleophile. And this nucleophile contains a lone pair or a pi bond, okay? Now, when we go through and we look at this reaction, I want us to look at a specific example here. So let's say that you have that alkyl halide reacting with this molecule. As you come here and you think about how this is going to react, there's a few things that you need to recognize. This bromine is very electronegative. So the halogen is the first thing. When I look and have to show a mechanism, the very first thing I scan for is that leaving group, right? And so I go through and I say, look, I know halogens are great leaving groups. Halogens are really electronegative. That's going to be partially negative. It's going to withdraw electron density from this carbon. It's going to make that carbon partially positive. That can be a reactive site there, okay? Now, over here, I look and say, all right, what could this be and can it react with this? It has a negative charge that indicates to me it's a nucleophile. So we previously talked about how to identify nucleophiles and electrophiles. And so we're using that in this mechanism. So now we're going to draw an arrow to show the bond formation from the nucleophile to the alkyl halide. So we have the electrons here on the nucleophile, and they are going to come and attack that partially positive carbon. When they do that, the bond between the carbon and the halogen breaks, and those electrons go onto the bromine. Now, follow your arrows because they're going to tell you what you form. And so when we come over here and we follow that arrow, we know that we are going to form, we're going to leave everything else the same, right? Nothing else changes until we get to this arrow here. And we say, okay, now we're going to have a new bond to that OCH3. So we say, all right, we got OCH3. And that's our product. And then we've also formed a bromine ion here that's got a negative charge. So that's what we're looking for. Let's do another example, okay? And with this example, right, I want to point out and remind you that nucleophiles here are going to be either negatively charged or neutral. So we talked about that in a previous screencast. Now, if it is negatively charged, it will have a counter ion that is with it or shown with it a lot of times. So what you'll see is something along the lines of this. Right? Where there'd be a problem like this. And so what you have to do is you have to recognize that's a counter ion. It's like a spectator ion. It is not going to participate in this mechanism. And you know that this is sodium hydroxide. That breaks apart into the counter ion and the OH minus. And that OH minus is going to be your nucleophile. So you need to rewrite the reaction here to show the mechanism and predict the product. And so the way we do this, right, is this. We're going through the exact same thought process. This is very electronegative. That withdraws electron density and it makes the carbon that's attached to that halogen partially positive. Positives and negatives are attracted to each other. So that means these electrons are going to go attack that partially positive carbon, forming a new bond. These electrons are going to go down on the bromine, right? And that bond will break. And so we follow our arrows. We look at this and we say, nothing changed here, nothing changed here. And we draw that over here. And then we get to that red arrow and we say, okay, right, something has changed here. There's a bond that's been formed with the OH. And then we think about the bromine. And then you always want to double check your charges, because remember, if there's one charge here, there's also going to be a charge here. So make sure you're double checking that your charges are correct. So we always want to be double checking our work as we go through. Now, we've looked a lot at these negatively charged nucleophiles. Let's look at an example of a neutral nucleophile. Well, maybe. Hold on. All right, now let's look at a neutral nucleophile. Okay, so when we look at a neutral nucleophile, actually I want to draw this like that. So there's our alkyl halide. Right? And there's a neutral nucleophile. Now, we can recognize this because it's got a lone pair of electrons here, okay? So it's neutral, but we have a lone pair of electrons, and that should scream to you nucleophile. So we go through the same analysis. We say, okay, here's our alkyl halide. This is partially negative. That's going to make that carbon partially positive. These electrons are going to come, and they're going to attack that carbon, and those electrons are going to go onto the bromine. When this occurs and you write it, you're following. You don't change anything that's not involved in the mechanism, so we leave that the same. Then we come here, and this is where we see our red arrow, and we're going to form a new bond to the nitrogen, and then we are going to have those 3 methyl groups off of it. But look, this is now a positive charge, because if you calculate up the formal charge of nitrogen, it now gives a +1. And this is still going to be a -1. Here. And I want you to double check your charges still balance, because +1 and negative, right, is neutral over here. It's 0. And there's no charges over here, so that's 0. So those also balance. Now, when a substitution product contains a positive charge and a proton, the product is going to lose a proton through a second step, which is a proton transfer mechanism. Okay, so I want us to look at an example of this, because that's not a concerted mechanism, and so we would see something that's a little different there. So let's look at this example. Actually, I want to draw it like this. Okay, so when we look at this, we identify our alkyl halide. We say, okay, this has got the halogen on it. That's our alkyl halide. We come here, we say, okay, that means that's going to be partially positive, and that's going to be partially negative. We come over here and we say, what is this? This is a nucleophile because it has these electrons. So those electrons are going to come in and attack the thing that's partially positive, because those electrons are negative and they are attracted to things that are positive. These electrons are going to go on the bromine. When this happens, right, that's your nucleophilic substitution. Okay, we're going to draw the products. We're going to leave everything alone that is not involved in the mechanism. Okay, there we go. And then this is not involved. Okay, now I get to a blue arrow at that carbon. And so now that's where I'm going to form my new NH3. And now nitrogen has 4 bonds, so it's carrying a positive charge. And that bromine is going to have a negative charge. Now, when that NH3 carries the positive charge like that, it's going to immediately go through a second reaction, a second step, because there's a positive charge with a proton on it. And so it's going to go through a proton transfer. Where another molecule of the ammonia, there's plenty of those ammonia molecules running around, right? There's lots of them, is going to come in, and it's going to come over there, and it's going to steal a proton. Oh, I don't like that color because I want it to stand out. There we go. It's going to come over here. It's going to steal a proton. Those electrons are going to go right back on that nitrogen. When it does this, we no longer have that positive charge. And we've made NH4 plus here. Okay. Now, this is where looking at the charges to see whether they balance or not becomes a little harder, because we have 2 steps here. So that's where that kind of double check breaks down a little bit. All right. So we have introduced in this screencast alkyl halides, as well as one of the reactions they undergo, nucleophilic substitution reactions with proton transfers. In the next screencast, we are going to talk a little bit more about the leaving group, and then talk about this idea of basicity and nucleophilicity, and see how they're the same and how they're different.